So in the previous session we have discussed about the tokens, lexemes and patterns, right? So we have discussed first the whatever input is there, so that will be divided into the lexemes, right? Suppose the position equals to r1 plus 60. So what are the lexemes here? The position is one lexeme, this one is one lexeme, r1 is lexeme, 60 is one lexeme. So this will be go to the patterns, right? So if the input string is matched by the patterns in order to generate the tokens, then only we can say this is a token, right? So the input string must match one pattern, then only we can generate the tokens. Okay, so these patterns, whatever patterns we are saying here, this should be given here. You can see that the topic is regular expressions and finite automata. So we already I think you already studied this regular expressions and finite automata in the ATFL subject, right, in the previous semester. So in the ATFL subject you have discussed the regular expressions and finite automata, but now how we are using this regular expressions and finite automata in the compiler design. So in order to generate the tokens from the lexemes, you need to have one pattern. So these patterns will be defined by regular expressions. Okay, so now here we are using the regular expressions in order to define the rules to generate the tokens, right? So how we are I told you that regular expressions are used for the to define the patterns, where we are using the finite automata. So we will define the patterns by using regular expressions, right? But in order to implement it, the regular expressions whatever we are giving here, the patterns, we need to implement it, right? So in order to the input we here we are giving, right, we only define the rules here, but that should take the input and it should generate one output. Here we are generating rules or conditions by using the regular expressions, that but this regular expressions should take the input string and it should generate one output, right? So for this one we are using finite automata. So this is for defining and this is for implementation. Okay, so I'm not going through this concept as you already know this already concept, so I'm not going deeply this concept. I'm just give you the small example. So I already told you to describe the tokens we will use the regular expressions. What are the regular expressions? So in order to define the regular language, we will use the regular expressions, right? So this is a symbol which will have the input characters. It will have the set of characters. The sigma is nothing but the alphabet. This is a alphabet which will contain the input language. The language over the string over the alphabet is nothing but the set of strings of the characters drawn from the alphabet. So whatever we are having in this one, suppose we are having AB, so the language, whatever the patterns or anything, that should be covered in this one only. Okay, and you can say that the alphabets are nothing but regular English characters and the language is nothing but English sentences. For the programming, for the computer, it is like alphabets are ASCII characters and the language is C++ programs, Java programs, C# programs, right? And the language are set of strings, and this needs some notation to specify which sets we want, right? So we are having the language because we are taking the input from the high level language, right? So that should be understood by the system. So first, in order to generate the tokens, that is also in the high level language, In order to generate those, we need to have one notation. So that notation is nothing but here regular languages. So in order to define these regular languages, we are using regular expressions, right? And here you suppose it is a. If a is a regular expression, suppose take it as a regular expression, and we write L of a. That means language described by a, the language that is described by the regular expression a. Okay, so I think these all you know, that or either or yes, either this R followed by S, concatenation of R 0 or more times. The star value represent the 0 or more. The plus symbol will be like 1 or more. The question mark is 1 or 0 or 1. So this is only the grouping, right? So if you are having the string this one, that means it can be A or B or C, right? So if you are having A to Z, means A or B or C, like up to Z range. So suppose these are some examples of the regular expressions. This is a regular expression A, and the strings we can draw from this regular expressions are A only, because we are only having one symbol, that is A. So AB is a regular expression. The strings in the language of this L of RE are AB, and A or B means we can generate the two strings here, A or B. Here A, B whole star. What is the star mean here? 0 or more. More times you can generate this string. So I can generate AB. I can generate AB one time and AB 2 times. I can generate nil also. It is like epsilon, you can say, because here we are including 0 also, right? And now here this is one small another example, A or epsilon and B. So for here you can say A, B, because I am taking here A first and this B should be there, A, B, and second one is B. So these are the strings that are in the language of these regular expressions. So for the integer and for the digits, these are the some examples for the regular expressions, right? So I already told you we have defined the patterns by using regular expressions, but this regular expression, such a mechanism is called the acceptor. This mechanism, you can say, we need mechanism to determine if an input string W belongs to the language of R, the language denoted by the regular expression R. Regular expressions we have defined, right? But we need to see that the input string, whatever we are taking the input string, is it accepting by this regular expression or not. So that will be generated by this one acceptor. So this acceptor is nothing but finite automata. So it will take the input string and the language, and it will be go to this finite automata. If it is belongs to this W, the string W is belongs to language L, means we can say yes. If W belongs to not belongs to L, means we can say no. Okay, so that is a finite automata. For the specification you use the regular expression, and for the implementation you use the finite automata. So the finite automata includes 5 symbols. One is sigma, the input alphabets, and second one is the set of states. Okay, set of states, and third one is a starting state, transitions, and the last one is a final state. Okay, so you can see it is one state, it is a starting state. The starting state should have this one, starting one, and this is a final state. Okay, so the transition nothing but from one state to another state, this input symbol is going, right? So if you are the input string is containing A, so it should have 2 states in order to pass this one. So from one state to another state it is going, right? So the finite automata accepts a string if we can follow the transition labeled with characters in the string from the start state to the some accepting state. What is the accepting state here? That is the final state. So whenever you are saying that the input string is